right, so this mini lecture is going to be an introduction to the idea of waves. So what is a wave? Now, oftentimes waves are taught in physics right after or very shortly after simple harmonic motion. So either with simple harmonic motion or shortly after simple harmonic motion. And they have similar properties, but they're not the same thing, and that's really important to understand. So if you've already looked at the simple harmonic motion lectures, right, that was our description of periodic motion. So this repetitive motion, like a pendulum that an object is moving through, or an object bouncing on a spring, kind of a periodic motion that we've described. It is described mathematically as a wave, but a wave itself is something different. A wave is something that is traveling, that actually goes through something, moves outward from a source, or moves along the shoreline if we're like talking about boat waves. So it doesn't go back and forth, right? It just continues to move in that outward, we'll say, outward direction. They have similar properties, and you're going to hear some terminology that's the same as you did in the discussion of simple harmonic motion, but they're fundamentally different. So the first thing to know, to really kind of embrace this idea, is that a wave is a transfer of energy through a medium. So that's the first thing I want you to know about kind of that definition of a wave. So a transfer of energy through a medium. So what's a medium? Oops, kind of talking and writing and getting my words mixed up. A medium is just like we use it in the art world, right? Different materials that artists work with, we call mediums. So different materials that waves travel through: air, water, on a string, through a material. Okay, so that's what we mean by medium. This transfer of energy through a medium in which it disturbs the medium itself, and then once that energy passes through the medium, is left undisturbed. So the medium itself doesn't move with the wave. The medium is just disturbed, and then it passes through. So you can imagine you're laying around in the water, and a boat comes by, and that wake makes a wave towards the shore. And as you're kind of waiting, let's say you're laying on your little dinosaur floaty, and you're in the water. So here's our water. And a wave comes by. You notice that when the wave comes by, I'm just going to draw, there's my dinosaur floaty again. It's happy, and as the wave, not too low, as the wave moves through you on that, you rise up on that dinosaur floaty as the wave goes by, but as the wave continues on, it's a very simplified version, right? You go back to where you were. So you, the medium, the water is what the wave is going through. We're going to use you as representing the motion of that water, moves as the energy goes by, as that wave goes by, but you remain relatively undisturbed after the energy goes through. That's very different than periodic motion, where it's going back and forth, right? All right. So how do we represent a wave? And here's where some of those similarities are going to come into play. How do we represent a wave? Here I was showing what we call a wave pulse. So we're going to talk about a wave pulse, and then we can talk about sort of periodic waves. And most of our behavior, our characteristics are going to be in periodic waves. That's a term that's familiar to you with simple harmonic motion. So what's a wave pulse? A wave pulse is simply a disturbance of the medium that has motion along that medium. So energy is given to a medium, and that energy transfers along the medium. So imagine that you are, you have a string attached to a wall, and you just flick the end of that string up. We know if we flick the end of that string up, we're going to get a little bump, and as time goes on, that bump will continue to move down the string. So this is what we mean by a wave pulse. Okay, this is a wave pulse. So that energy translates along the screen. Again, if we examine this particular location on the string, the wave moved through it, that particular element of the string remains undisturbed after that wave has passed by. So that's what we mean when we talk about wave pulses. And when we look at superposition, we'll use a pulse to help us gain our ideas and develop our ideas about superposition. So I want you to be familiar with a wave pulse. Try to use this a little faster. Doesn't erase as well, but get us there. All right. And the second is this kind of periodic waveform. And that's what we really kind of think of a wave. If I told you to draw a wave, I'm going to guess you would have drawn a wave that looks like this. All right. And we also use this representation, of course, for a simple harmonic motion. So here's where some of the things are going to be similar. Now, let's talk about similarity first. The first is kind of how fast that wave is going in its up and down fashion. Like simple harmonic motion, we describe the wave both with a frequency and a period. And you may recall, and if you aren't watched the simple harmonic motion videos, of course going to tell you now, frequency is as if we were standing and we were counting the number of cycles that went by us. If I'm standing letting this wave move by me, 1 cycle, 2 cycle, 3 cycle, 4 cycles, move by me in time. How many cycles per second? So what's a cycle? A cycle, keep in mind, is when we go through a complete wave motion. So if I'm starting here at the bottom, and this bottom we call the trough, and this top, you might imagine we call the peak. All right. If I'm starting at the trough, a cycle would take me up and back down to the trough. Or if I'm starting at the middle, a cycle, middle on the way down, right? A cycle would take me down and up and over and back down. One entire waveform, regardless of where I start. That's what we refer to as a cycle. So frequency is the number of cycles per second that a wave makes in that amount of time, seconds. So this is cycles per second. It has units of 1/2, and those units are also known as a hertz. A period is also related to the time it takes for a wave to complete a cycle. Slightly different. In the case of a period, it's as if I'm standing there and I'm watching one cycle go by, and I hold a stopwatch and I see, okay, a trough went by, start, and as that wave goes by me, I see the next trough, stop my stopwatch. How long it takes for a cycle. So a period is how long a cycle is. All right? And that's time, so it has units of seconds. Now, it's how long per cycle, seconds per cycle, and frequency is number of cycles per second. Hey, those are related. And so we know that the frequency is equal to 1/the period. Or the period, these are equivalent, is equal to 1/the frequency. So that gives us a sense of the timing of a wave. That's related to simple harmonic motion. So that should sound familiar if you've been through simple harmonic motion. But we also might be interested in some of the dimensions of the wave. How tall is the wave? How long is the wave, right? How tall is the wave? How long is the wave? So those are different. How tall a wave is measured from the center of the wave to the peak, or from the center of the wave to the trough. And this is what's known, of course, as the amplitude. And this is the physical height of the wave. Similar to in simple harmonic motion, the amplitude was that peak-to-peak distance that the object traveled in its periodic motion on one side or the other. So amplitude, similar to what we did with simple harmonic motion. And the last, that's kind of a new piece, is what we call the wavelength. How long is this wave? This is the wavelength. We use the Greek letter lambda for the wavelength. All right, we use the Greek letter lambda for the wavelength. How long that wavelength is, that's given to us in a length dimension, so that's in meters, and our amplitude is also in meters. All right, so these are some properties of the wave, and we can use these properties to look at another property that's actually very interesting for us, and that's how fast does a wave move. So in another mini lecture, we're going to dive deeper into wave speed, but I want us to think about how wave speed might be related to these other variables here. Wave speed, like any speed, is how fast that wave is moving. Now, what do we mean by how fast? I don't mean how up and down it's going, but remember, this wave is moving in an outward direction. Let's say this is the source. So it's moving away. Wave speed is how fast is it moving away from us, linearly. So, how might that be related to some of these other things I have here? Well, the wavelength is how far the wave travels. So if I imagine I have a particle, and we're going to visualize this because a wave, remember, is a disturbance of the medium. So this particle isn't actually moving, right? It's a disturbance of the medium. But let's for a minute imagine that this particle was moving with the wave. Doop, 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 doop. And I get to this other wavelength. It has covered a distance equivalent to the wavelength. In how much time? Well, peak to peak is 1 period, so it covered that distance in 1 period. So the distance per period gives me that distance per time speed relationship. Now, I'm going to be a little bit careful with us. So distance per time we know is equal to speed. And I said the time is the period, but keep in mind 1 over the period, 1 over the time is the frequency. So this gives rise to our wave equation, a very important and useful equation for wave speed, which tells us that the wave speed is the wavelength times the frequency. And we're going to use that in a much deeper dive in the wave speed and problems traveling, waves traveling on a string in another mini lecture. I want to give you a sense of all of the properties to be thinking about in terms of how we describe waves. All right, good job.